Okay, good evening, everybody. Today it's our pleasure to have Professor Satyanarayana Reddy with us. He works in spectral graph theory and algebraic graph theory. He is an associate professor in Shivnadar Institution of Eminence, Delhi NCR. We're very happy to have you, Satya. Yeah, over to you.
Yeah, thank you for giving the opportunity. Yeah. Okay, so the title is adjacency algebra of a graph because most of the time I'll work with adjacency matrix. You already started actually, Rajesh Khan sir already started. So it is a powers of A. Adjacency algebra may simply mean that not only A, all powers of A and a vector space containing all these set of all polynomials in A I will take that forms a vector space as well as it has a ring structure. That is adjacency algebra. I'll introduce it later slowly. What is the advantage of having adjacency algebra? So you already discussed, listening from morning. Yeah, adjacency, by using adjacency matrix and its spectrum, we can find many properties. You have adjacency algebra also extra thing, you can get more information. Okay, we'll see these things as time progress. So I will start where actually in the last class stopped. Okay, so that is bipartite graphs. Okay, so let me start that. Okay, so there are 4 lectures. It will go like this. Okay. So in the previous class, as you know, Sir discussing with you the bipartite graph, right? I took the complete bipartite graph. Okay. So you have already observed that the matrix look like, right? 0, right? Here O meaning 0 matrix here and 0 matrix this side, B transpose, right? In the last previous session, you are looking that. But in this case, it is a complete bipartite graph because of that all ones will be there. Okay, so it is indexed ABC here. Okay, and sorry, 1, 2, 3, 1, 2, 3 ABCD, 1, 2, 1, 2, 3 ABCD, right? So there is no edge between ABC to AB, 1, 2, 3 to 1, 2, 3. So that's why this is 0. And here you have ones and all that, right? Okay, what is this spectrum? In the previous lecture, you are discussing this part, right? Eigenvalues are symmetric about origin, right? Here, 0 is an eigenvalue 5 times and root 12 and minus root 12, they are eigenvalues with the algebraic multiplicity 1. Okay, why these are? Okay, you all know that adjacency matrix is a symmetric matrix, right? So symmetric matrices are diagonalizable, okay, that you are already discussed, okay. That means it is diagonalizable. Diagonalizable meaning, so it is similar to a diagonal matrix. Then automatically, what is the rank of the matrix? Okay, so I'll ask some questions one by one now. So I'll ask one question to all of you. If you want to answer, can you tick yes? What is the rank of a diagonal matrix? Can you tick yes if you want to answer? What is the rank of a diagonal matrix? Be quick, please. What is the rank of a diagonal matrix? If you do not know, tick no, that's okay. Not an issue, right? Okay, Divesh, can you unmute and speak? Divesh Kumar Singh. Yeah, unmute and speak, Divesh. Hello, Divesh.
Yes,
Okay.
yes, sir.
Yeah, can you tell me what is the rank of a diagonal matrix?
The order of that matrix.
No, it cannot be. What is the rank of a zero matrix?
It is 0.
I can take a 10 by 10
Yeah,
zero, right? Yeah. Okay, no
yeah.
problem. Bhagyalakshmi,
Yes, sir. It is equal to number of non-zero eigenvalues.
a non-zero eigenvalues. You told directly the answer. Okay. Actually, it is the number of non-zero elements in that number of non-zero diagonal elements, but diagonal elements are the eigenvalues. So rank of a diagonal matrix
Eigenvalues.
is equal to, yeah, you can mute now. So rank of a diagonal matrix is equal to number of non-zero eigenvalues. Now that is extended for diagonalizable matrix also, right? Now my adjacency matrix is a diagonalizable matrix. That means that rank of the matrix equal to number of non-zero eigenvalues. Now what is the rank of this matrix? Somebody can say, you look at the matrix here. Can you say what is the rank of the matrix? Yes. Now you can say, Somebody can you unmute and say
Sir,
what is the rank?
Rank is 2.
Yeah. True, right? Yeah, it is 2, right? So rank is 2, meaning number of non-zero eigenvalues are 2. The matrix size is 7 by 7. That means, so 2 non-zero eigenvalues. Remaining all are 0, right? So the multiplicity of 0 as an eigenvalue is 5 here. Okay. Now how to find these 2 eigenvalues? Without actually solving the problem, I came to know that 0 is an eigenvalue 5 times, right? With the multiplicity 5, because it is diagonalizable. The diagonalizable, okay, rank equal to number of non-zero eigenvalues, right? From that I came to know. And the next
Sir.
thing is, yes, please.
Sir, good evening, sir.
Yeah, please. Yeah, good evening. Please go ahead, please.
Sir, I have the doubt, sir. The zero matrix will have the rank, sir.
Zero matrix, rank of the zero matrix is defined as 0. The definition itself, okay? Yeah.
Okay.
Is it okay?
Okay.
Yeah, thank you for asking. Yeah. So eigenvalues of a now I am extending it. It is a complete bipartite graph 3, 4. In general, what is a eigenvalues of complete bipartite graph, right? For that also rank is equal to 2. That means that 0 is an eigenvalue how many times? Somebody want to comment? For KMN, complete bipartite graph, unmute and speak. 0 is an eigenvalue how many times?
Mn minus 2.
How many? What is the size of the matrix? Yeah, okay, good. M plus n minus 2. Okay. 0 is an eigenvalue, m plus n minus 2 times. Now 2 eigenvalues are non-zero. How do you find them? That is the question, right? Okay, so that is done. So lambda 1 and lambda 2 are the remaining 2 non-zero eigenvalues, right? That we need to figure out. How do you find them? So trace of the matrix equal to 0, because morning I think Rajesh Kans are already discussed with you. Since it is because we are looking graphs only, undirected graphs, right? No self loops and all, right? Simple graphs, because that trace is equal to 0. And the trace is nothing but sum of the eigenvalues. So lambda 1 is equal to minus lambda 2. And also you know that a square, in a square, what are the elements? Number of arcs of length 2, right? That means actually diagonal elements are automatically the degrees of the vertices. Okay, because of that. So now, but the trace of a square equal to lambda 1 square plus lambda 2 square. Okay, but lambda 1 equal to minus lambda 2. Because of that, 2 lambda 1 square equal to number of edges. Sum of the degrees equal to twice the edges, right? Number of edges are mn. So we'll get root mn. Okay, so I'm clearing all feedback here. If you are clear with, please click tick yes. If there is any doubt, tick no. Are you clear with till now? Can you tick yes? Are you clear with till now whatever happened? Okay, good. Thank you. So I'm moving forward, but I need more response. Okay. Yeah. Okay. I'm moving forward now. Okay. So spectrum of that is called spectrum. Spectrum of KMN is equal to square root of Mn 1 time, root Mn 1 time, and 0 m plus n minus 2 times. Okay. Yeah. Okay. Now look at this. This graph you already know, right? It is a complete graph, right? What is a complete graph definition? Somebody asks you, there is an edge between any 2 vertices. Any 2 vertices are adjacent, right? Okay. Now, what are the eigenvectors of this? Okay. So you can easily check that these are the eigenvectors. 1, 1, 1, 1 in an eigenvector. We'll again discuss it later. For every regular graph, the 1, 1, 1, 1 become an eigenvector that can be seen easily, because in each row we have same number of ones, right? So because of that, 1, 1, 1, 1 vector become an eigenvector, because when you multiply any matrix with 1, 1, 1, it gives the row sum, right? All row sums are equal if the graph is regular. Okay, that's why always 1, 1, 1 is an eigenvector, and these are other eigenvectors. I will tell you how these come. These also came, and the spectrum is for this 4 and 4 is a eigenvalue, because that is the degree of the vertex. It is a four regular graph. So 4 is an eigenvalue with the multiplicity 1. Minus 1 is an eigenvalue 4 times. Okay, how these came? How we get these eigenvectors? What is the adjacency matrix of the complete graph, right? In the complete graph, everywhere we have ones, right? Except the diagonals, right? So that we can denote as J minus I. J means all ones matrix. Okay, are you clear about J matrix? J meaning all ones. Throughout this course, not only me, everyone will use J. Okay, do not forget that. Okay, J minus I is the matrix. Now, what are the eigenvectors of? What is the rank of J? Somebody can comment. J means all ones matrix. Everywhere
One.
1, 1. Yeah. What is the rank? Yes, please.
One.
Divya Devi.
Rank is
One.
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 Ah, is it symmetric matrix?
Yes.
If it is symmetric and then it is diagonalizable,
Yes.
so then what is the number of non-zero eigenvalues?
One.
Two.
One only. That
One.
means all other eigenvalues are 0 for J, right?
Zeros. One.
Yeah. So, but what is that eigenvalue? Only one positive eigenvalue. What is that? That is n itself, right? You can easily check that. If you multiply 1, 1, 1, 1 vector, right? You take a 2 by 2, okay? 1, 1, 1, 1, multiply with 1, 1, okay? Vector with 1, 1, right? Then we'll get 2, 2, right? 2 times 1, 1, right? Okay, that is always an eigenvector. What about other eigenvectors? So in the previous class, I already discussed with you that symmetric matrices, we can find an orthonormal basis, right? That means already I know one vector 1, 1, 1. That means all others are orthogonal to that. That means if I sum them, that is equal to 0, right? You can see that here vectors 1, minus 1, 0, 0, 0. If I add them, it will be 0, right? These are all orthogonal to my 1, 1, 1 vector. Okay. Yeah. So fine. So you know eigenvectors of J now. What are the eigenvectors of I? Anyone comment? What are the eigenvectors of I? Identity matrix. Is anyone want to comment?
One, sir.
Eigenvector. Eigenvalue is 1.
Okay.
Eigenvector. What are the eigenvectors of identity matrix?
Standard basis.
Every vector is an eigenvector.
That is the answer you need to tell. Every vector is an eigenvector. Of course, standard basis, obviously. Standard basis you told, then it is not you told in giving so many vectors. Please try to answer exactly what I am asking, right? Okay, that is good. I'm happy with that. My point is not finding mistakes. My point is that you need to go in that way also. Okay. Yeah. It is because in future you will attend interviews and all. So people ask those things also. Are you listening the question properly or not? Okay. Please do not think otherwise. Okay. Yeah. Okay, good. So you understand that that is a beauty. Every vector is an eigenvector. Then for J minus I, what are the eigenvectors? Every vector of J can be eigenvector of J minus I also. That means what are the eigenvectors of J and complete graph? Complete graph is J minus I. Is it every vector of J become an eigenvector of complete graph? Yes or no? Can you take yes if it is yes? What is my question? What is it I'm saying? Every vector of J is an eigenvector of complete graph. Every eigenvector of J is an eigenvector of complete graph. Do you agree with that? Response is very poor. Can you please tick? So J matrix, you understand all ones matrix, right? Yeah, Sarita ji, can you unmute and say? Sarita? Yes, Sarita ji. Okay, right. Okay, yes, okay. All eigenvectors are same. Okay. Yeah, without your response, how can we move? Okay, please try to understand that. Okay, eigenvectors of J are eigenvectors of the complete graph also. Okay, yeah, okay. We'll move forward. So now you understand the eigenvectors and then eigenvalues also, right? All other eigenvalues of J are 0, right? We'll get -1 as an eigenvector. Very easy. Okay. So that's why spectrum of Kn is n minus 1 one time, -1 n minus 1 times. All eigenvalues are non-zero because of that. And another beauty is that only one positive eigenvalue, all others are negative. Okay. Okay. So now this is the problem. What I'm going to do with you is this. Okay. So in the last two examples are very easy. There it is easy to find out what are eigenvalues, eigenvectors also. Eigenvectors in the last class, last lecture, Sarah discussed with you in KMN case, bipartite graph, right? You already know, okay? You remember x1, x2, then x minus x1, x2 is an eigenvector corresponding to minus lambda, right? So for some graphs, easy to find out eigenvalues and eigenvectors, but in general, it is tough. So what is the techniques? That is problem 1. So problem 1 is that if simple undirected connected graph is given with n vertices, okay, because y connected I'm taking, disconnected graph will connected components का spectrum, okay. So it is that is union of the connected components. So better to confine to connected graphs, okay. So many properties of X such as you already discussed, okay, regularity, bipartness, connectivity, so many things of related to graph can be obtained from the linear algebra. So in particular adjacency matrix. So we are using the techniques of linear algebra to find the properties of the graph. Many things can be found, but if X is large, finding spectrum is very tough. You know that from degree 5 onwards, it is difficult to find the roots, right? So it is very difficult. Okay, then what to do? So one technique is that we need to find out another matrix, condensed version of A, smallest size, and finding the eigenvalues of that. Okay, that is problem 1. Problem 1 is that how to find eigenvalues of A. Instead of finding eigenvalues, I'll find the eigenvalues of the some other matrix, condensed matrix. Size is very small. For that, I'll find. What is that? I will discuss. That is my problem number 1. Is it clear? Problem number 1 is clear. I'm not asking question. Now, can you take guess? Is the problem 1 is clear to you? Just asking that is the question clear? Okay, thank you. Good. Okay. Now the question number 2 is that, okay, there's another thing. A graph y is said to be a polynomial in other graph, right? That means adjacency matrix of the one graph is a polynomial in the adjacency matrix of other graph. Then you know, if I know the eigenvalues of a matrix, then I know the eigenvalues of its polynomial also, right? P of lambda 1, P of lambda n. That means that if I know eigenvalues of one graph, I know the eigenvalues of other graph, provided one graph is a polynomial of other graph. Okay, now this is the question. So what are all graphs which are polynomials in a given graph? If I know that one, then I can find eigenvalues for many graphs. Okay, so but there is a nice thing that if my graph has a nice properties, regular properties, then from adjacency algebra that I will define later, I can find all the polynomials in X. What are all graphs which are polynomial in X? That we can easily find out. Then I can found eigenvalues for many graphs by using this graph eigenvalues. Okay, this is problem 2. Okay, so please think about, and now clearing the feedback. Now again, tick. Can you tick, please? Is it the second problem is clear to you? Problem 2 is clear to you. What is the problem 2? Given a graph X, meaning adjacency matrix is given. I am finding all those graphs which are polynomials in the X. That means polynomials in the adjacency matrix. Okay. Okay, this is not clear to you, many of you. Okay, fine, no problem. We'll discuss it. Okay, I'm clearing and I'm going back. Yeah, so these are the problems. Both problems are related to partitions. Partition of the vertex set in particular. You know, partitions are related to equivalence relations, right? Okay. So problem 1 related to the partition of the vertex set V. Problem 2 related to the partition of the vertex set V cross V, not vertex set. Sorry, there is a mistake here. It is not vertex set, it is V cross V. Okay. So group actions provides a partial answers to both the problems. What are group
I'm
actions?
sorry to interrupt you, sir.
Yeah,
Could you
please.
repeat question number 2? I couldn't get it immediately.
Sorry, can you repeat, please?
Yeah. Could you please repeat the question number 2 again?
Question number 2. Yeah. Okay. Question number 2. Thank you for asking. Question number 2 is that I gave one graph to you. I have one graph with me. Now my question is that what are all graphs which are polynomials in this graph? What do you mean by one graph is a polynomial in other graph? Okay, that is, one graph is given and then I have an adjacency matrix of that graph, right? Then I take the polynomials of that I take different polynomials and substitute A. Then I'll get a adjacency matrix of other graph. Okay, what I want to say is that adjacency matrix of Y is a polynomial in the adjacency matrix of X. Okay, somehow I able to, so the adjacency matrix of Y, there is a polynomial such that adjacency matrix of X, if I substitute in that column, I'll get adjacency matrix of Y. What is the advantage of that? What is the advantage of that? If I know the eigenvalues of X, I know the eigenvalues of Y. Because if I know the eigenvalues of one matrix, I know the eigenvalues in every polynomial of that matrix also. Okay.
Got
For
it.
example, eigenvalues of A are lambda 1, lambda 2. What are the eigenvalues of A square? Lambda 1 square, lambda 2 square, right? What are the eigenvalues of 2A? 2 lambda 1, 2 lambda 2, right? If you take any polynomial in A, eigenvalues are simply the polynomial in that. Am I okay or not okay?
Yes, sir, it is clear now. Thank you.
Yeah. Yeah. So I'll explain you this. Actually, before starting, I'm just telling you that these are the two main problems. Entire my 4 lectures are revolve around. Yeah. Okay. Yeah. So good. Thank you. So any other questions? Okay. Thanks for asking. Any other questions? Okay. So there is something called group action. What is a group action? Group acting on a set. If you have a graph, then there is something called automorphism group of that graph. We'll discuss that. Okay. Automorphism group of the graph acts on the vertices. It also acts on the V cross V. That will give the partitions. Orbits will come, right? Those who know group actions, they know orbits. Orbits partition the set. Those orbits are going to help us. Okay. So that is what I'm saying here. So knowledge of automorphism group and group actions are very useful for us. Okay. Now I'm going to the problem 1 now. Okay. So the problem 1 is that so one nice partition called equitable partition of the graph. Okay. So first problem I told you that it is a partition of the vertex set. Okay. So now try to understand that. So okay, cool. Nothing happened till now. Okay, so I take a partition V1, V2, Vm of the V. V is a vertex set. I partitioned it. You know partition meaning. Their union equal to whole of V. If I take any two of them, intersection is empty. But which partition I want? Not all partitions are equitable, right? Then there is no meaning of definition. Okay, a partition is said to be an equitable partition if it satisfies some conditions. What are those? Okay, so if I take a V1, V2, Vm is a partition, right? Okay, so I take a one vertex U belongs to Vi. Vi is one cell. Okay, I'm calling V1, V2, Vm are cells. If U is in Vi, then I will count Bij of U, number of neighbors of U in Vj. How many neighbors of Vi are in Vj? Okay, okay, that easily count. That may be 0 or any number. That is always possible. But that a partition is said to be equitable or regular partition if Bji of U is independent of the concrete choice of U. That means if you take any two vertices in Vi, it has exactly same neighbors in Vj. Okay, it is true for any I and j. Okay, so okay, right now it may not be fully clear to you. I will discuss it and I'll give lots of examples. Today, lots of examples only. Okay, so what is an equitable partition? It is a partition of the vertex set in such a way that if I take any vertex in V1, okay, it has same number of neighbors in any vertex in V1 has same numbers of neighbors in V2 or V3 or sorry in V2. Okay, and same number of neighbors in any two vertices in V1 has same number of neighbors in V2. Means that number may be different. For V2 it is same. Okay, I'll explain it. It is depends upon I and j only. Okay, I'll come to that clearly. Okay, so that matrix now it is independent of the vertex chosen. So we'll get a matrix that is called quotient matrix. Okay, this is the condensed matrix now. The size is very small. So we'll prove that I can get eigenvalues of A from B. B is a very small matrix, and eigenvectors of B will give eigenvectors of A also. I will discuss these. That is the idea today's session, right? And this most of the content I taken from Gardsell and Royal. Okay, algebraic graph theory book by Gardsell and Royal. Okay, yeah. So okay, so let me explain now, right? What are these things? Okay, right. Okay, now this is the starting point. You can say. I hope you all of you looking the graph, right? Okay, look at this and I will keep silent for some time. What are observations you observe? Please let me know. Okay, take time, 30 seconds time. Somebody want to comment, comment. Whatever you understand, whatever you noticed, please let me know. Because if you notice, it will stay for a longer period and you will enjoy it. If I speak, then you will understand. That is accountant job, just you are verifying whether I am saying correct or not. But if you see it, it will be very useful. That's why I'm giving time to you. But don't worry, any mistake happen, let it be happen. Because you don't know, you are just you are checking whether your observation correct or not. गलत होते तो होने दो, कोई दिक्कत नहीं. If there is a mistake, no issue. With mistakes or something, we'll learn it. It is not mistake first of all. Your observations, I'm asking. Anyone want to comment?
One for a degree 3 and other degree 2. That's it.
Sorry, can you say something?
1 and 4, what is a degree 3?
Wonderful, correct. That's why this is called regular partition also. 1 and 4 have the same degree, yes. And all others have degree.
Yes, sir. All others have degree.
Degree how much? Others have degree?
Others are degree 2.
Degree 2, that is the thing. So that helped me that, okay, I'll separate these two as one partition of the vertices, right? So 1, 4 I put here and 2, 3 remaining vertices I put here. Okay, good observation. Any other thing? Any other observation? What is I done now? Okay, I now I relabeled the vertices. Okay, I put the adjacency matrix like this. Why I divided like that? Now this is a block matrix, right? Blocks. Okay, each block is a matrix. Do you see something in the blocks? Some observation can you make in each block? Yes. Any observation? If I say, then it is not interesting, right? You see the first two rows. Do you observe something in these two rows? Yeah, constant.
Constant row sum.
Very good, constant row sum. What about here? This last block. Constant row sum, right? Row sum is 1, 1, 1 everywhere. Here also you see 1, 1, 1 everywhere. Here it is 0, right? So we divided if it is a regular graph, I no need to do this. All of them are already constant row sum, right? It's a beautifully we divided like that. Am I clear about it till now? Is it all of you understood that? Can you take yes, please? Can you take yes, please? So only 4 or 5 ticking. Okay, there are around 50 students out there. Okay, that is a problem with MSc and so we are all students. I am also a student. Okay, do not assume that. Yeah. So okay. Anyhow, thank you. So those who are giving feedback, I'm thankful to you. Okay. So look at here. Can you see vertices? What is that I done here? What are these V1, V2? This is a set now. It is not one vertex. Are you able to see that? V1 is actually 1, 4. V2 is that 2, 3, 4, 5, all those. Okay. 2, 3, 5, 7, and all that. Okay. These vertices are now vertex set, subsets of the vertex set. Why I put 3 here? Somebody can point out 1 here. Something can you say? Can you comment?
Row sum is 3.
Row sum
3
is
edges.
yeah, there are various ways. Yes, row sum is 3. Wonderful. Okay, but row sum is 3 is okay. That is one way to look at. Okay, why here it is 1? Okay, yeah, somebody else is saying edges. Please, can you please again say more about that?
Every vertex in V1 adjacent to exactly 3 vertices of V2.
Wonderful.
And,
Sorry.
and
Yeah.
when we look at V2 set, so among those vertices, it is adjacent to exactly one of the vertices in V2.
Okay, Divya Devi, thank you very much. Yeah, see what she is saying. You see that 1 adjacent to how many vertices? in the V2. V2 is a set of vertices, right? V2 is 2, 3, 5, 6, 7, 8. And 1 and 4 are in other set. Okay, you take any vertex in V1, that is 1 or 4, you have same number of neighbors in this set. Okay, there are only two sets. You take 1, 3 neighbors are here. 4 also 3 neighbors. That is independent of the 1 or 4, right? Similarly, you take 5 or 6 or 7 or 8. How many are in V1, right? For example, you take 5. How many neighbors V5 has in V1, capital V1, right? Only 1, right? 6 also only 1. 5 is adjacent to 1, 6 is adjacent to 4, 3 is adjacent to 4, and 2 is adjacent to 1. Okay, that's why V2 to V1 I put 1 here. Okay, it is called quotient graph. I am quotienting it. You know that whenever you do partition, you will get a quotient, right? Whether you take vector spaces or a group theory, whatever you take, right? We'll do partition so that, so I will, I am treating all of them are same, right? Yeah, okay. So what is this matrix now? Somebody can point out this matrix now. V1 to V1 0 is there. V1 to V2 3. V2 to V1 it is 1. Can somebody point out that? Comment on that.
But it is adjacency matrix of this quotient graph.
Sagar, sorry, actually your voice is breaking. Can you repeat, please? Yeah, repeat. What you said is correct, but everyone not able to listen that. I hope so. I'm thinking that.
I was saying that is it the adjacency matrix of this quotient graph?
Like that quotient graph. It's a little bit of like that. So what are the, but here V1, okay. Vertices are V1. That is a subset of V, right? How many elements in V1 are adjacent to V1? That is 0, right? So V1 to V2, that is 3. Okay. That is independent of the vertex. Then only I can have this, right? Different vertices have different neighbors, then I cannot have this. If you have, then only that is called equitable partition. Then only I have the proper definition. Okay. Yeah, good, nice. Okay. So now now it is easy to find eigenvalues for this matrix, right? Okay. Because you know characteristic equation for this 2 by 2 matrix is lambda square minus lambda minus 3, right? Then you can find eigenvalues. Now I'm telling that these are eigenvalues for my original graph also. And even the spectral radius are going to be same. Okay, spectral radius we can find by using Perron-Frobenius theorems are about to start today, right? I will tell at the end later. Okay, so first example may be clear, not clear to you. I'll go to the next example, right? So I'll show next example. I hope you will concentrate and say something now. Can you see it? Can you comment? Take some time, 1 minute time. Please let me know. Okay, so I'm clearing your feedback. Once you are clear, please tick yes. Once you are done, you understood, tick yes. Okay, what we are doing here, I divided the vertex at 8 vertices are there. I divided into 4 parts. 1, 3 is 1, 2, 4 is 1, 6, 7 is 1, 5, 8 are 1, right? 1, 3, how many edges are there? How many neighbors are there, right? So 1, 3, you see that 1, 3 to 1, 3, there are no edges, right? 0, right? That is that row sum is 0. Constant row sum 0. That is comes here 0, right? Matrix side also you can take in terms of neighbors also you can say, right? So 1, 3 to 2, 4, 2, 4, right? How many neighbors are there for 1 in 2, 4? Only 1, right? No, 2, right? So 2. So that's why 2 came, right? This number, do not look at this matrix, okay? Look at 2 directly here. What is this 2? So this set 1, 3, how many neighbors in the 2, 4? Okay, 1 is adjacent to both 1 and 4. 3 is also adjacent to both 2 and 4, right? That's why 2 came. Okay, so am I clear or not clear now? Is it okay? Yeah, okay, nice. Now we got a 4 by 4 matrix. Now it is a quotient matrix, right? Okay. Okay, I'm moving forward. Still, if it is not clear, this example, we'll see more examples. Don't worry. Yeah. Okay. So I hope I will move forward, but
Excuse me, sir.
yes, please. Yes.
Sir, in the definition of equitable partition, we have that we have partitioned the vertex set like V1, V2 up to Vm, and M is strictly less than M.
Sorry.
So,
B1, B2, Vm we divided. Yeah.
and M is there strictly less than M.
Obviously, because it is a partition, right?
Like yes, it is partition. Can we not have only a single element in a partition?
That can be there. That we will discuss. Is it an equitable partition or not? Good question. Yeah, that is the important thing, right? In that case, what happens if all of them are singleton? Okay, what is that matrix I get? Is it not same as the adjacency matrix? How many cells
Yes.
are there?
So,
Right?
it will
But there
be
is no use. There is no use, right?
number. Yeah.
Yeah,
But
you are
I
correct.
think that
No, you told very beautiful point actually. Very, very beautiful point that every vertex set has at least one partition now. Partitions, equitable partitions are non-empty, that you told. Okay, whether it is useful or not, that's a different case. Okay, we'll discuss that. Yeah, are you okay? Are you clear about?
yes,
Yeah, thank you. Okay, good. So can I move forward? Since anyhow I'll share this material, you can understand this, or you tell me something, or you want me to discuss this also. Can I move forward? Okay, what is happening here is that see, 1 and you take 1. Here I put 1, 2, 3, but these are not these 1, 2, 3. Okay, yeah, actually these vertex at V1 like that. Okay, so this 1 meaning 1 and 2. Oh, so how many neighbors are there? 2, right? So 1 has 3 neighbors. See, 1 has 3 neighbors in the yellow, right? Orange, you can say, right? 1 to 5, 1 to 7, and 1 to 3. Okay, and 2 also have the same thing. And with blue, it has 2. 1 is adjacent to both. Okay, 2 here. That's why 2 came. Okay, and green to red also it is 2, right? 9 has 2 neighbors in red. Okay, hope colors and everything is clear to you. And we have this is the quotient matrix. Okay, so this partition is an equitable partition. Okay, right. Any questions still you have? Okay. Okay, now get back to another. This is a good example, easy example, right? And you can find already we done something as well. He already pointed out, he guessed. Okay, these singletons are is always an equitable partition, right? That we already discussed just now. Okay, now V1, V2, Vn itself is an equitable partition, entire set. That means that there is only one cell, right? If you take any vertex, it has to have equal number of neighbors. When that is possible, when the graph is regular. If the graph is regular, entire set itself is an equitable partition. Am I clear about that? So I'm clearing the feedback. So please tell clearing the feedback. Then can you take yes, please? Are you clear about it? Okay, good, nice. Okay, thank you. Yeah. Okay, so at least one equitable partition is a singletons, but that is no use. I'll give more examples later. But full set is also equitable for only it is regular graph. In that case, you know that the quotient matrix become that regularity K itself. That is an eigenvalue also. From here also we are proving that regularity is an eigenvalue, right? K regular graph, K is an eigenvalue. Okay, so that is a beauty. Okay, Now look at this matrix. You know this is a complete bipartite graph, and people also call it star graph, right? So here we have this part, okay? So we have this. Yeah. Okay, so here this is one cell, only singleton, and you can easily observe, right? So 1 to 1 there is no edge. 1 to 1 there is no edge, right? 1 to these, how many edges are there? 5, right? 1 to this is 5. Okay. Now here to one, only one edge, right? But among them 2, 3, 4, 5, there's no edge. That's why 0 here. Okay. Yeah. So this is the graph. Now what is the, now can you tell me what are the eigenvalues of this matrix? All of you can check easily, because trace equal to 0. What is the characteristic polynomial for this matrix? Sorry. Somebody can tell me what is the characteristic polynomial for this matrix? Trace is 0, right? 2 by 2 matrix. Unmute and speak.
X square minus 5 is equal to 0.
What are the roots now, eigenvalues?
Plus or minus root 5.
We done it na first slide pe, what is that we studied? Kmn, right? It is K15. What are the eigenvalues of Kmn? What are the eigenvalues of Kmn? Root mn one time, right?
Plus
Minus root mn one time. 0 is the remaining eigenvalues, right? We studied it. Na?
Yes.
Yeah, so here 1, 5, right? So root 5 minus root 5 and plus root 5 are the eigenvalues I'm getting from this. Okay. You got an evidence, right? The small matrix is giving the eigenvalues of my original matrix. Are you okay? Are you clear about? Is it not beautiful? It is very beautiful, right? Even this work now, we can extend it to data science people, whatever they say, buzzwords, right? You have an image, big matrices, right? Is it possible to convert into smaller matrix and find eigenvalues and to the bigger matrix? It is giving an ideas, right? Okay. So let us go. So see the same graph. Now I'm giving another equitable partition. Okay. Equitable partition need not be unique. Now look at this one, right? What I done here. So here 2 is there. I'll brought to this side. Okay. Hope you understanding. So 2 adjacent to 1. Now 1 is adjacent to, of course, 2 already. 3, 4, 5, 6. The same graph, but another equitable partition. Okay. Why it is an equitable partition? Here there is only one cell, so no need to worry. Okay. So how many neighbors? 2 and 1. Okay. This is singleton. This is singleton. Okay. There is only one, right? 2 to 2, 0. 2 to 2, 0, right? 2 to 1, only 1. Okay. 2 to 3, 4, 5, 6. There are no edges from 2 to 3, 4, 5, 6, right? That's why 0. Okay. First row is clear to you. Hope it is clear. Now look at the 1. Okay. 1 is adjacent to how many in this? Only 1, 2. 1 to 1, 0. How many neighbors are there in 3, 4, 5, 6? 4 are there. That's why 4. Okay. Now 3, 4, 5, 6. Is there an edge from 3, 4, 5 neighbors? For 3, how many neighbors in this first set? 0. 4 also 0. 5 also 0. 6 also 0. Okay. How many neighbors in this orange? Only 1. Okay. Among themselves 0. So this is the matrix. Now you can see that here first row and last row are same. Okay. It is a rank 2 matrix. Okay. Now you get all the eigenvalues of my matrix. Okay. Yeah. So are there any doubts in this? Okay. One more thing you observe here, what I'm done in this particular case, it is called a distance partition. Earlier one also distance partition. I take one vertex, all the neighbors I put here. Now what are the neighbors of 2? Nothing are there. So I stopped there. Here I started at 2. What are the neighbors of 2? 1, right? I hope you understand. 2, only one neighbor, 1, right? Now what are the neighbors of that? So now you know that diameter of this graph is 2. Diameter of this graph is 2, right? I can go up to 2 length, right? Diameter 2. Okay. So this is the partition and it is an equitable partition. This partition is called distance partition. So all 2 is one vertex, distance partition with respect to 2. All vertices at distance 0 from 2 is 1, that is singleton. Distance 1, 1. Distance 2, 3, 4, 5, 6 are distant distance 2. This is called distance partition. Sometimes the distance partition of a vertex may give the equitable partition, but not always. Are you clear about this? Okay. Not only that, here each vertex is giving ka distance partition is giving equitable partition, but they are not equal. Okay. When for each vertex they are equal, then they are called distance regular graphs. Okay, that is the part of my portion, right? That we will discuss later. Okay, right now is it okay? For one graph, more than one equitable partition, and what are those? Okay. Just I'll give some pause. Do you have any questions or something you can ask? How to pronounce Ajendrana? Ajendranar. Okay, yeah. So, what is her nickname? Ajen? Ajigan.
Alagendra. Alagendra.
Alagendra.
Alagendra. Yes.
Okay. Alagendra. Okay. Thank you. So, okay. Look at this. It's a beautiful example. This graph, you know, anyone of you know this graph? I'm clearing feedback. Now, can you take guess? If you know the graph, can you take guess, please? Is anyone of you know this graph? Very famous example. When you say famous example, you recall, right? Okay. So those who tick yes, I will ask one of them, right? Yeah, Preeti Prasanna Mandal.
Peterson graph.
Peterson graph. Thank you. Yeah, it is called Peterson graph. Okay. Now you see the beauty that I'm giving different types of partitions here. Okay. One partition is that all outer are 1. Okay. 1, 2, 3, 4, 5, outer 1 and inner 1. It is an equitable partition because you look at any vertex here. How many neighbors are there in the green one, right? One has how many neighbors? Only 1. Okay. You take that is independent of the vertex you choose in the outer. Okay. Similarly, inner. So every inner have 2 inside and 1 outside, right? Yeah. Okay. Yeah, that is what V1, V2. So V1 to V1 also 1 is there. V1 to V1, red to red. There are 2 are there, right? V1 to V1 self loop. That's why it is put as 2. V1 to V2 1, V2 to V1 1, and V2 to V2 again 2. Okay. And the quotient matrix becomes 2 1 1 2. Okay. And eigenvalues we can compute. Okay. So actually eigenvalues of the Peterson graph, 3 distinct eigenvalues, -1, 3, 1, right? Okay. So this is 2 by 2, I'll get 2 eigenvalues only, 1, 3. Okay. Here it is a distance partition. Okay. Second one is a distance partition. What I done, I first start with one vertex. You can take any vertex, don't worry. I start with 1. What are the neighbors of 1? 2, 6, 5, 6, 2. They are neighbors. Then, so it is the diameter is 2. I'm going distance 1, distance 2. Okay. So they divided according to the distances. That's why distance partition. Distance partition with respect to 1. Okay. Yeah. Am I clear about distance partition? Okay, good. Okay, I'll move forward then. Okay, so now you see that it is a graph. This graph is regular. All of them together also will form 1. Okay. And then the quotient matrix is size 1 by 1. And 3 is an eigenvalue. Okay. 1 by 1 matrix eigenvalue is itself. That is also eigenvalue of my graph. Okay. So regular graph 3 is regularity. Correct. Okay. Okay. Now we'll go to how to find these things. Okay. So there is a beautiful linear algebraic approach to characterize equitable partition and all. So sometime now I'm away from the graph theory, only matrix theory. Okay. Yeah. So let us see that. So irrespective of that. Okay. So I will wait for some time, 1 minute time. Whatever you noticed in this, it is easy now. Very, very easy. Okay. It is independent of the graph theory. Okay. You please comment. Whatever you noticed here, you tell me. Very easy. From this, you can easily figure out. So 30 seconds time to you. So somebody want to comment, initial thing also fine. Okay. Generally in my class, I will wait for all the students because in regular class, what happens now? Ajendra, yeah, can you go ahead?
Sir?
You say whatever you observe. Say, yeah, whatever you notice. What is this
From
pi?
first partition, pi
What
is a partition. Is a member in the symmetric group.
No, that is not okay. Don't go into symmetric group and all. So sorry for that. Not maybe by looking pi, you are thinking it is a symmetric group and all. No, just it is a partition. Okay. How many
Yes,
cells? How many cells are there in this partition?
Two members.
2 cells are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay.
6, 7, 8, 9.
So I divide into 2 groups. Their union equal to whole set and intersection is empty. It's a partition.
Yeah.
No doubt.
Yes, sir.
No, everything clean. What is this P?
P is
Anyone else?
Is a kind of
Anyone?
adjacent symmetry.
No, it is not adjacency matrix. There is no graph theory.
No.
Yeah, don't worry. You can unmute. You can mute now. Somebody else can comment. Whatever you understand, let me know. Yeah, thanks. You discussed. Any other person? Anyone?
So those elements are in the first partition. They are connected one means given number one. And then second partition, these elements are there. They are one.
Right, you are correct. Is it Raghavani? No, actually somebody else.
Rangaveni, sir.
Rangaveni, but
Yes.
you are not speaking, right? Rangaveni
No,
is
sir.
not.
No, sir. No, sir.
Preeti Kosanna Mandal speaking.
Okay, Mandal, yeah. So Preeti, so actually I thought that it is a male voice, so Preeti is there, so I confused. I'm sorry for that. Okay. Anyhow, get back to the problem. Yeah, so that is what is that vector called? 11111 That vector has some name. Anyone know? That is called characteristic vector. Why characteristic? It is characterizing 1, 2, 3, 4, 5. Okay. So 1, 2, 3, 4, 5 belong to that set. So 1, 1, 1. So 2 cells, so 2 row, 2 columns. Okay. When this is in this, it is in the set subset, then I'll put 1. Otherwise 0. Right? Okay. Now what is that I'm done? P transpose into P. Okay. Okay. P transpose into P I done. Okay. So you notice that 5005 came. Okay. Because can you say something about these 2 columns also? Anything else you want to say? These are characteristic vectors. That is fine. Can you say something about these vectors? Anything, any comment you want to make?
Orthogonal.
Orthogonal. Yes,
Orthogonal.
they're orthogonal. Wonderful.
Orthogonal.
Okay. Yeah, what is P transpose into P generally we do? Okay. See, when you have a P transpose into P, I will not multiply 2 matrices actually. Here I written like that, but actually P transpose mean P meaning you doing the dot product of the same row, right? Dot product with itself. Okay. So you see that this is multiplied here, right? This first row multiplied to first column, but first column is nothing but row of P only, right? Because of that, so we are doing dot product of the rows. What is the dot product of first row with itself? That is 5. What is the dot product first row with second row? 0, because they are orthogonal, right? Dot product second row with itself 5, right? So please think that way. P transpose P easy to compute. It is the dot product of the rows. No need to multiply 2 rows and all. Okay. Even though I written here. Am I clear about that? Okay. So what is this 5, 5? Somebody comment? What are these 5, 5? Okay, these are exactly the elements in that partition.
Eigenvalues. Okay.
Yeah. No, of course, eigenvalues of that matrix is 5,
Okay,
5.
okay, okay.
But yeah, but these are exactly the how we
El-
partition the set. 10 elements I divide into 2 groups, right? The number of elements in each set, each subset. Okay. One more beauty is that since it is invertible, right? Diagonal matrix 5, 5. So its inverse also, you know, right? Inverse is also 1 by 5, 1 by 5, right? Then I take the inverse and multiply with P transpose 2 by 2 and 2 by that matrix. So you got a matrix like this, right? Can you see something about, somebody comment about this matrix? Of course, here rows are orthogonal. That is clear. Anything else?
Sir, if this P transpose V whole inverse P can make equal to the diagonal matrix.
No, not that part. So you understand that P transpose P is 5005. Its inverse is
Yes.
1 by 5. This is clear.
Yes.
Multiplied with P transpose. This is P transpose. So 2 by 2 and 2 by 2 by 10. So I'll get 2 by 10 that we got. Okay. I'm selling. Can you say something about these 2 rows? Any comment you want to make? By looking this matrix.
Orthonormal.
Yes, please. Yes, please. Yes, please.
Orthonormal.
Orthonormal is anyhow there. That I already informed. Other than orthonormal.
We get the elements of the in the given matrix only, sir. 1 by 5, 0, 0, 1 by 5.
Okay. That is okay. Any other?
1 by 5 is eigenvalue of P transpose P.
That is okay. That is anyhow there. 1 by 5. So, but okay. What is the row sum? First row sum.
1.
Tomorrow, I think Marco process mein sir will discuss these things with you. Okay.
First row sum, second row sum.
What is first row sum?
1.
1.
1, right? Second row sum.
1.
1. They are called row stochastic matrix. Okay. Row stochastic. Okay. Probability vectors. Okay. So it is independent, right? Very simple problem. 1 to 10, we divided, we partitioned, and we took the characteristic matrix. All these things came, right? I hope there is no confusion. I hope. Okay. And anyhow, slides will be available. You can check later also. Right? Yeah. Now I not stopped here. I multiplied n also. I multiplied with P further. Okay. P into this particular thing. So I got this. Can you observe what is this matrix now? Of course, I written here already. Can you see now? What is the row sums?
Adjacency matrix.
No, it is not adjacency matrix. There is no graph at all. Please try to understand. Abhi, right now, no graph theory. I took some set 10 and partitioned it, right? Ekdam cool, nothing. Okay. So I took partition and I got the two columns and P. Why 2 columns? Only two cells are there, right? So I'm just calculating all of them and I'm asking you to observe things, okay? That become theory later, right? What is the row sums here?
It is row sum
1.
and column sum both are 1, so it is doubly stochastic matrix.
They are doubly stochastic matrix. You see that you take any set, any partition, okay? You choose any set, any partition, not only 2 parts, you can take many parts, okay? Finally, you multiply P transpose P, will get a doubly stochastic matrix, okay? Now, how do you check a given partition is an equitable partition or not? One result is this, n commutes with A. Now graph theory coming. I have a graph A, I have a graph X and whose adjacency matrix is A. Now I take a sum partition, whether it is equitable or not, right? I'll compute this and I'll calculate this. Okay. It is not a easy one I'm saying. Okay. In the morning, I think a second lecture or sometime you will discussed polynomial complexity, right? So to prove something, there are different algorithms will be there. So this is one algorithm whether to check a given equitable partition is an equitable or not given partition. but I'm not saying this is the best, okay? But it's a beautiful idea that equitable or not, if and only if condition. We are not proved anything, okay? Just I'm telling the facts now. Okay, because examples only will guide us that how things will come. Okay. Okay, this you not understand. This is just a statement only. Okay. Now let us work one more example. Okay, please go through it. Please go through this. Again, no graph theory, nothing. I have a set 8 elements. I took a partition. Okay. These are called cells of the partition. 1, 4, 6, 2, 5, 7, 8, and 3. Sorry, earlier I told V1, V2, Vn, so that is related to vertex set. But we can restrict to C1, C2, Cm only. Yeah. Do you understand that characteristic matrix P? C1 is a column. Okay. Do not please do not confuse with this capital C1 and this small c1. Column 1, column 2, column 3, column 4. Okay. Column 1 contains 3 ones. Okay. Where there are ones are there. Okay. Are you able to see them? Yeah. Okay. Good. Okay. So you notice that what is P transpose into P? C1 transpose into C1, right? They're orthogonal. Na? You already told they're orthogonal. Then only diagonal will be there. Remaining are all 0. What is C1 transpose into C1? What is the dot product with itself? That is number of cells, right? 3, 2, 2, 1. What is this 3, 2, 2, 1? That is the number of elements in this cell, right? Am I okay? Are you clear about? Can
Yes, sir.
somebody unmute and say, please? Is it okay? Here? No, I need your response, okay? One is that you can tick yes. Otherwise, you can unmute and speak. Okay, thank you. Good. So no doubts, no confusions. Okay, we'll move forward. Yeah. Okay. This is another example, right? This I will discuss more detailed way, right? Connecting it to graph theory also. 1, 2, 3, 4, 5, 3, 2, 4, and 1, 5 partition of S. Okay. So then you understand, na? 3. So at 3 it is 1, 2 and 4 1 1, and 1 and 5 it is 1. So right. If you add all the entries, I'll get the cardinality of S. Okay. So P transpose into P, you understood. Okay. So we'll get number of cells, and all these are clear. Okay. Yeah. I hope no need of explanation here. What I done earlier, I have done the same thing. One more example, so that finally you will get this N is a doubly stochastic matrix. Each row sum column sum is 1. Okay. Now, is there a graph with this partition as an equitable partition? Okay, we will in a while I will tell that every partition is an equitable partition for complete graph. I will tell that in a while, but we look for a non-trivial graph. Okay. Okay, look at this. Okay. You know, anyone know what is this graph is? Can unmute and speak.
Path.
Path graph, right? So path graph may I take 1, 2, 3, 4, 5, and a distance partition I took with respect to vertex 3. Distance partition means at 3, what are the neighbors 2 and 4? So they are at a distance 1 from 3. 1 and 5 are at a distance 2 from 3. That is called distance partition. Partition with respect to distance, right? That is an equivalence relation. Okay, I and J are related if their distance is 1, like that we can make, right? Okay, so it is a distance partition. Is it an equitable partition? Yes. Okay, that is what I done earlier. Okay, you can check that. We'll get this matrix. Okay, now this matrix commute with my B. Sorry, not this one. Okay, 1 minute. Go slow now. So this is the path graph, and I consider distance partition, and you have this, right? Now here I brought A here. Okay, so I'll go back. So P transpose P inverse into P transpose, this matrix you got. Okay. Now for that I'm multiplying with A. Okay, what you get? We get some matrix like this. Don't worry, what is this and all? Okay, we'll get back to that. And multiply with P also. Okay, finally this entire thing. You get the B. B is the quotient matrix. You see the beauty? If it is an equitable partition, I'll get my quotient matrix. So P transpose P inverse, diagonal matrix inverse into P inverse. I think I made a mistake here. Somebody point out. It is not P inverse. What is this? I'll change it.
P
Somebody
transpose.
P transpose. Yeah, sorry. P transpose. Right. Okay, we'll get B. Okay. So actually, how we'll get it? You try this. AP, A is this and P is this, right? Okay. You'll get matrix like this. That is also easy to check. Easy to check. What is happening here? Okay. So, okay, go through it. I'll talk to you. PB. You see that AP equal to PB you got. These are observations. We'll prove it now. P is that characteristic matrix. A is the adjacency matrix. B is the quotient matrix. If it is an equitable partition, AP equal to PB. Proof is given here. Don't worry. Do not read this now. Okay. Why these two are equal? Okay. Yeah. So let us see. You know that A is indexed by the vertices, right? I take a vertex U. Let us say some 3, vertex 3. Okay, like that. You take some vertex. Okay. Then you are multiplying here, correct? Okay. So when what happens? Ujth entry of AP. Ujth entry meaning what? I take uth row, jth column, right? Here I take uth row, u row u, right? And here some j column. If I multiply, what I'm going to get? Okay. That is exactly the number of neighbors of u in the cell Cj. Are you okay? Are you understanding? If u belong to Ci, then this number is Bij because it is a equitable partition. A little complicated here. Not all of you may not follow immediately unless you work. You start working, then you will get it. See, look at here. This is 3, right? 3 is adjacent to 2 and 3 is adjacent to 4, right? Now, if you multiply this one, what happens? I'll get 0, right? Here I'll get exactly 2, right? That means this 3 is multiplied to 3. 3 to 3 is 0, right? 3 to 2, it is 2. That is exactly these numbers, okay? Yeah. So that is what is happening. Here it is much easier. Okay. What is this 0, 0, 1 if you multiply to any matrix? What happens? Can somebody tell me that if I multiply 0, 0, 1, first row to the matrix? Zero, 0, 1, first row multiply to this matrix, right? What I'll get?
Third row.
So third row go to first row, right? Are you following? 0, 0, 1 I multiplied, 0, 0, 1 I multiplied, 0, 0, 1 I multiplied, right? First row, this third row become first row. That is actually, it is shifting. Okay, what is this do? This do will do when you multiply. Second row
Will be shown.
Yeah. What is this will do? First row will come. What is this will do? Second row will come. What is this do will do? First row will, last row will come. Right? So these rows only repeated. Are you following that? These rows only repeated.
Yes.
Yeah, very easy. That is easy to see. Now these two are equal if it is an equitable partition. Okay. Yeah. So please make an attempt. If not now, go through this. Okay. So I'll get back to this again. Okay. Yeah. So what happening is that AP equal to PB, then I can multiply both sides with P transpose also, right? And then I can also multiply with the P transpose P inverse also both sides. Then I'll get B. That is the reason by doing all these things. Okay. Okay. Yeah. Okay. So look at that. So this is an example here for to explain that whatever I done till now, I am taking this example one more time. In complete graph, every partition is an equitable partition. Every partition. Okay. That you can check slowly. Right. Yeah. So I gave the reasons also for each concept. Okay. You can work it out and later. Yeah. Now we'll try to prove all these things, whatever we observed till now. Okay. For that, you need to understand one concept in the linear algebra. If W is a invariant subspace of Rn, A is an n by n matrix, real matrix. If W is A invariant, okay, so W is a subspace. Then it has some basis. Y1, Y2, Yk is a basis for W. Then we can construct a matrix P with Y1, Y2, Yk as a columns. Okay. Yeah, this is independent topic now. This P is not a characteristic matrix. Okay. But I want to connect. That's why same P I took. Same A I took. This is not adjacency matrix. It is general setup now. Okay. Since W is A invariant, A Yi again belong to W only. W is invariant subspace. AYI is in W. Therefore, AYI can be expressed as a linear combination of vectors of the basis again, right? So that means that this AYI is equal to P times BI, some matrix. Each one is giving one coefficients, right? So what I want to say that A into P is equal to this AY1, one column we get, AY2 again expressed as linear combination of Y1, Y2, Yk. So this is easy to see. So we'll get some, these are the coefficients, right? PBI. AYI is equal to PBI. AYI is again belong to WI. That means that it is a linear combination of the Y1, Y2, Yk. That's a PBI. Okay, right. You know that PBI meaning it is a column space, right? That is in the column space. Hope you know these things. So if you want, I can explain further, but I'm moving forward. Okay. That means that actually this is a beautiful thing will come. It is in general true. W is the invariant subspace of A and P is the matrix formed with the basis of W, then AP equal to P into B, some B. B is the coefficients. Am I clear about this? I know that morning onwards you are listening. Little. Am I clear? Can you take us, please? Yeah. Okay, good. Thank you. So we'll move forward. Okay. Now, if X is a graph with adjacency matrix, say pi is a partition. So pi is equitable if and only if the column space of A is A invariant. Okay. That we saw AP equal to PB we are getting already, right? So that's why A invariant. I just because of that I gave this. Okay. Now we'll go through. Okay. Please go through it and again next class you can ask me. Okay. Don't. It is not end of the thing. Okay. Okay. Now look at the beauty here. You can see something here. Okay, this is another thing. So you can go through. The beauty is that the quotient matrix, what we got, that is need not be symmetric, but it is similar to a symmetric matrix. That is a discussion here. This paragraph is about that discussion, right? Okay, what is I'm telling as a fact, like here I gave the explanation, but I'll come back if time permits because I started at 4:15 or so, 4:10. So I have another little time. So 10 minutes around I have. Okay. Okay. So what I'm telling here is that the quotient matrix need not be symmetric, but it's similar to a symmetric matrix. Okay. Then why symmetric matrix? I'm telling similar to symmetric matrix. Eigenvalues are real. I'm telling that eigenvalues of B are eigenvalues of A. A is symmetric matrix, right? That's why just a problem. But without that also we can handle now. Do not understand, don't worry about that. But this is useful. You see that this partition I took earlier, when I multiply with x1, x2, x3, what is happening? See, when the theory comes, they even Godsil book not explained all these things. Why they will explain, right? Okay, we need to sit down and work it out. The reader has to work it out. Yeah. So that's why I give all of them, all the ingredients here. You know that entire class I am discussing only one concept, equitable partitions, right? Yeah. Okay, look at this. This is a partition. You multiply x1, x2, x3. What is happening? Can you notice that? Somebody can comment. I discussed earlier also, but can you see what is happening? What is the size of this matrix? 5 by 3, correct? 5 by 3 multiplied to 3 by 1. What I will get? 5 by 3, 3 by 1.
5 by 1 matrix.
5 by 1.
Output.
What is the elements actually? You see the beauty that what I'm getting. Because these are each row has only one. Are you see that? Haina? That is happens, right? Each row has only one. This is related to cells. Right? When you multiply, I'll get only one vector here. So 0, 0, 1, x3 will come here. Okay. And can you see here what is happening? x3 how many times came? 2 times. x2 2 times. x1 1 time. Why 2 times and x1 only 1 time? Can you see that? In the partition 1, 2, 3, 4, 5, 3 comes only 1. This is a cell with only one element. X3 comes, so X1 comes only once. Okay. 2, 4, 2 times. Okay. 2, 4, 2 times. So X2 2 times, 2 and 4 pay. Okay. X3 3 times. Are you okay? Are you clear about? So that means that they are constant. When you multiply any vector, they are constant on the cells. Are you okay? That is the main point. They are constant on the cells. Okay. Yeah. Now get back to the problem, actual problem. So AP equal to PB, right? We already noticed if equitable partition, P is the characteristic matrix, then AP equal to PB. From that, is it easy to see that when what happens if I multiply by A on both sides? A square P equal to APB, right? Do you want me to write? Is it okay? Yeah, okay. So actually it is not visible where I'm. Okay, sorry. Where I'm writing, here I'm writing. Okay. What I want to say that, see, no, something is problem. Okay, sorry for that. Okay. Let me try one more time.
Actually, there is a type. A power kp equal to p into b power k.
Can you repeat, please? Can you repeat?
Yes, actually, there is a typo. By induction, we can see that a power k p equal to p into b power k.
Okay. Correct. Thank you so much. Is it okay? Correct only or not? Okay, let us see. A square p multiply by a square p equal to AP. AP is PB. Okay, correct. You are correct. Yeah. Okay. Thank you. You are correct. Okay. I hope everyone that mistakes also advantage sometimes, right? Yeah. Okay. Thank you for pointing out this. Yeah, it is P into B power K. That means that not only when you multiply 2 also same, right? In fact, any polynomial you take f of a into p equal to p times f of b, right? F is any polynomial. Now, if you choose my polynomial as f of a equal to 0, then p times f of b is 0, right? Yeah. Okay. Then what happens? But p is all columns are linearly independent. Okay. Then you'll get f of b equal to 0. That means whenever f of a equal to 0, f of b equal to 0. Okay. What is that suggesting? Right? What is that suggesting, right? Yeah, that is suggesting that the minimal polynomial of B divides the minimal polynomial of A. Are you understanding that? Therefore, the eigenvalues of B are eigenvalues of A. Okay. Yeah. In fact, now we're going to prove that. In fact, yeah. 1 minute. Actually, this is creating problem to me. Yeah. Okay. Right. Okay. So, in fact, we can show that actually characteristic polynomial of B divides the characteristic polynomial of A of X. Okay. So I'll prove that easily now. P is a characteristic matrix of a partition pi, and it is an equitable partition. X has n vertices, and Q be the remaining matrix whose columns together with those of P forms a basis of Rn. Okay. So what is the size of P? Size of P. Somebody can comment. Okay. Go slow. Maybe I'm a little fast earlier. I'll get back to the problem. We have a partition. Pi is a partition. Pi is an equitable partition for the graph X. Okay. In my course, I'm calling graph denoted by X because automorphism group I'll denote as G. Okay. In other lectures, maybe graph means G. Okay. So my graph is X, n vertices. So P is a characteristic matrix of pi. Then how many rows are there? Rows is equal to the n only, number of vertices. But number of columns equal to the number of cells, right? That is the cardinality of pi, right? Okay. And already you know that they are orthogonal. Okay. Now they are invariant under A. Okay, because AP is equal to PB. They are invariant under A, right? Then you know, I think Rajesh Kannans are already discussed with you. If W is invariant space for a symmetric matrix, its complement is also invariant under A, right? You know that, right? Can you somebody say yes or no? If W is invariant under A, then W perp also, that means orthogonal complement is also invariant under A. If you want, we can prove it. Okay. Okay, don't worry about that. Okay, forget about that. But at least do you know that I can extend the eigenvectors to full set? See, the columns of P are some vectors. They are linearly independent, right? Because they are the orthogonal. They are linearly independent. Can I extend them to form a basis for Rn? That is easy. Basis extension theorem. So that is called Q. So Q is also a matrix. Okay, but n cross that remaining part. Okay, now PQ together, you see here, the PQ together, they form the basis. Okay, now multiplying, so AP is equal to PB, AQ is equal to A into Q. You know that PQ together forming the basis, columns of P, columns of Q. These are the entire basis for Rn. Okay, okay, then AQ, when I multiply A, it is actually, this is a basis, na? P and Q are the basis. They are expressed as linear combination of the columns of P and columns of Q, right? So AQ is expressed like this, but AP equal to PB because it is a equitable partition, right? Then you will get this matrix, right? So AP is PB, AQ is PC plus QD. We'll get this way. Okay. Now PQ is entire matrix is invertible. Columns of P, columns of Q together full basis for Rn. It is invertible. I'll multiply. I'll get this. So what is that you noticed from this? Matrix A is similar to this matrix, right? Matrix A is similar to this matrix. And you know that similar matrices have same characteristic polynomial, right? But the characteristic polynomial of this is characteristic polynomial of B into characteristic polynomial of D, right? That means characteristic polynomial of B divides characteristic polynomial of A. Okay. Am I okay or not clear or clear? Please let me know. Okay, thank you. Thank you. Some of you are picking us. So that is very, very thankful to you. At least 3-4 people are there. They are following and clearing feedback. Move forward. So the beauty till now, what happened, if you have an equitable partition, the characteristic polynomial of B divides characteristic polynomial of A. Now I'll go quickly now. Not only characteristic eigenvalues, I can get eigenvectors also. That is the beauty. Okay. So we see that how to get eigenvectors of A from the eigenvectors of B. Now I'll tell you that. Okay. Last thing, climax. Okay. So suppose V is an eigenvector for B with an eigenvalue theta. Then BV is equal to theta V. We have that AP equal to PB. Then try with the PV now. P into vector. Okay. So is it possible? Is PV defined? Because size of P is n cross that cardinality of pi, right? That is the B is a square matrix, cells cross cells, right? Hope you can follow that easily. So PV is defined because P is a rectangular matrix, size will sufficient. But now PV size is that n cross 1. Okay. I hope you are following. Okay. So then APV. Okay. AP is PB, PBV. So theta PV. So then what is that you noticed? What is that you noticed? Can somebody comment now? Last only, don't worry.
PV is a eigenvector
Yeah, but what is V here? V is eigenvector for
of
B.
B.
Okay, eigenvector of B giving eigenvector of A. That is P,
Yes.
PV. But how PV look like you noticed earlier? You remember that I wrote earlier P into X. You noticed here? You take any vector, what is happening? That is constant on the cells, right? You noticed that? Okay. Then what is that you noticed now? How the eigenvectors look like? They are constant on the cells. It is not beautiful. Eigenvectors are we are getting eigenvectors of adjacency matrix are equal on the cells. If it is an equitable partition, eigenvectors are beautiful. They are equal on the cells. Okay. Anyhow, I am very happy when I see this. You also appreciating. Okay. Another thing is that the eigenvectors of V of P lift the eigenvectors of A. This is called lifting because V size is smaller, PV size is bigger. You see the beauty that the eigenvectors B is a quotient matrix. Okay, eigenvectors of B giving eigenvectors of A by equal values, repeating the equal. Okay, yeah, okay, right. Hope some of you are understanding it, appreciating it. Okay, not only that, now all eigenvectors from eigenvectors of B, I'm getting eigenvectors of A. That is fine. What about the remaining eigenvectors? That is also beautiful because now you look at that Q now. Q is there with us. In fact, my matrix A is symmetric. I can choose orthonormal basis. Okay, that means that all the eigenvectors of Q, all the Q vectors are orthogonal to P. Okay, all the vectors of Q are orthogonal to P. That means their sum on each cell is 0. Their sum on each cell is 0. Okay, that way you can get other eigenvectors. Okay, okay, I just wrote that part here. You can see here. Okay, so this is done. So the column space of P is A invariant, then so is its orthogonal complement. That is now my Q. Those are constant on the cells by, they are from PV. Those that sum 0 are on each cell is the other vector. So eigenvectors of A divided into two classes. They are equal on the cells 1 and sum is 0 on the cells. There are two parts. I will explain entire thing through an example so that it will be easy. Okay, with that I will stop today, right? My time is also up. Okay, yeah. So, so can you know this graph? It is called friendship graph. Okay?
Friendship graph.
Yeah. So friendship graph is that So it has a beautiful property. Here I'll give for so friendship graph here. It is so what is the definition? Okay, I should not draw the graph. Okay, friendship graph means that any two vertices have exactly one common neighbor. That is a definition. Any two vertices have exactly one common neighbor. Sorry, I shown the graph before, but this graph constructed after coming the properties. Okay, so it is called Dutch windmill graph also. So in general, Fk has 2k plus 1 vertices, 3k edges, and all that. Okay, the diameter is 2. Okay, yeah, okay. So, but these are all come only after drawing this. But before that, it is difficult. So there is. So what is that? There is a vertex. When this property is there, any two vertices have exactly one common neighbor. That is the definition. Okay, that much only definition. With that, we can prove that there is a vertex in which is adjacent to all the vertices. It is called friendship theorem. It is a beautiful theorem. Okay, that we need to be proved. Then only graph will be formed like this. Are you clear about? Okay, this is the property of Fk. Once we prove this, then star graph is a subgraph of Fk. Then the diameter is 2 is clear. Okay, that is fine. Now I want to tell you that how to find eigenvalues, eigenvectors of this graph. With that, I will stop as an application of the equitable partition. Okay, so I take only two cells now. Okay, cell C and AB, A1, B1, A2, B2. These are all other cells. Okay, be a partition of the vertex set. Two cells only. Right. So are you able to see that adjacency? Sorry, the quotient matrix is like this. Are you able to see that, please? Somebody can comment. Why 10 is there? 1, 1 is there. Somebody can comment that. Can you quick, please? All of us want to leave. C is one cell. C to see how many neighbors are there? 0. Right? C is adjacent to all other. 10 is clear. C is adjacent to all of them. So 10. Right? Here among themselves. Okay. So these cells to see how many? Only one. Everybody is a neighbor to see, right? And among themselves only one. Okay. In general, F2, Fk 0, 2k, 1, 1. Okay, then you can easily find the eigenvalues of this matrix, right? Characteristic polynomial is x square minus x minus 2k. We'll get the eigenvalues. Okay, right. Well, how to find the eigenvectors? Now, all eigenvectors I can find out. I'm not giving eigenvector corresponding to B now. I'm giving other eigenvectors. So B also have two eigenvectors, right? Corresponding to these two eigenvalues. That I can lift. I'm not talking about them. Okay, that you can figure out. I'm telling other eigenvectors. Okay, so look at here. Look at these things. What I done? A1, B1, I'm giving 1, 1. A2, B2, minus 1, minus 1. What is the sum? At C, I give 0. C value 0. C is 0. And remaining, I divide like that. Okay. What is the sum of all the entries now? At least in the cells,
0.
what is happening? 0, right? Yeah. So in the cells, it is giving 0 sum. Okay. A1, B1, 1, 1. A2, B2, minus 1, minus 1. Remaining 0. And C also 0. But at least in the cells sum is 0, right? Cells sum is 0, right? Yeah. Okay. That is what we want. That's why C also I gave 0, right? So these are the, like that I can shift them. These are eigenvectors. So these are eigenvectors for the eigenvalue k minus 1, right? And they are linearly independent. Sorry, they are k minus 1 are there and they are linearly independent with eigenvalue 1. Okay. And these are also sum is equal to 0, right? These are k eigenvalues with minus 1. So total k minus 1 and earlier already 2 are there. Total how many eigenvalues? How many distinct eigenvalues? Here 2 eigenvalues. They come from that one, right? And 1 and minus 1 are other 2 eigenvalues. Okay, are you following? So windmill graph has 4 eigenvalues only. 1, minus 1, and 1 plus or minus these two. Okay, yeah. Okay, that is the spectrum, entire spectrum. You see the beauty? Without actually evaluating, we got. Okay, yeah. So characteristic polynomial is this. Okay, so I will stop here. Okay, so you can ask any questions you have, right? Oh, am I not visible? Okay, visible.
Yeah.
Do you have any questions? Sorry, if you put chat, I will not see you. Okay, now I can see you. But I'm requesting that do not put in the chat. Okay.
Stop recording now. Yeah.
Yeah, you can stop.